So what we have talked about leads us quite naturally into the idea of entropy and the second law of thermodynamics. Entropy is a word that gets kicked around a lot, and we're going to give a very formal definition, and then we're going to end up using it in somewhat a hand-wavy way. So the formal definition here is the probability that a macroscopic state will occur spontaneously. And spontaneously doesn't necessarily mean like on its own, but from a random process, will this happen or not? And part of what I like about this definition is that you know that probability is a number. And in fact, entropy is a value that can be calculated. Here, we are talking about it in a conceptual way. That's all we will do in this class. But if you were to continue on in the study of physics, you would find that we can actually calculate entropy. So we're making a qualitative argument here. It can be made quantitatively, but that's more challenging. So we're not going to do that right now. So in general, the hand-wavy argument is that entropy measures the amount of disorder in a system. And the book gives us this nice picture trying to show what we mean by disorder. And we don't necessarily mean like just how messy is your room, but imagine that I have a bunch of atoms and that they're lined up, beautifully arranged like this, right? An OCD person's, happy place. The likelihood of gas atoms bouncing around and suddenly ending up in this configuration is really low. This is low probability of happening. This is high order. So this is actually low entropy, both from the first definition and the second definition. There's a lot of order, which means there's low disorder, and this is really unlikely to happen. Then you can think about them being a little bit displaced from it, but there's a lot of different ways they could be a little bit displaced. So this becomes more probable, and this has more entropy. Finally, we get to something that looks very random. How many waves can I randomly drop these gas molecules in this box? Well, almost an infinite number. And so there's a really high probability that something that looks equally random like this will happen. So this is high randomness, high entropy, high probability. So where this actually comes back to thinking about thermodynamics, think about separating hot and cold atoms, right? Pulling your hot atoms to one side of the box and pulling your cold atoms to the other. You could put a barrier in the middle if you want to. This would be fairly low entropy. This is actually order. Not necessarily the order where they are all arranged in an array, but you've done some sort of separation. If you then let them go, again, if there's a barrier in between, we've talked about how they can still transfer energy through collisions at the barrier, or they could just mix, right? So this is the idea, say you have red socks and white socks. You can really carefully pair them together and have high order of all of your white socks on one side of your dresser, all in their pair, all of your red socks on the other side of the dresser in their pair. But then, your roommate comes in and wants to torment you, and she unpairs them all and mixes them up, right? So that point, they're in equilibrium. That's high entropy, a lot of randomness. There's many different ways for your red socks and your white socks to be mixed together. And it's very probable that as she mixes them together, they don't suddenly end up white on one side, red on the other. So that's the idea here. Now, let's look at the second law of thermodynamics. And again, we're covering these topics only conceptually. There's not really a calculation associated with them. But again, later on in physics, there can be. So the second law of thermodynamics says that the entropy of an isolated system, or groups of systems that can interact but are isolated from everything else, never decreases. So you can say another way of thinking about this is that the entropy either increases or stays the same. And in this case, we're specifying that entropy is increasing until the system reaches equilibrium. Or if the system begins in equilibrium, it stays the same. So equilibrium is maximum entropy. So if you place your system in an equilibrium, it's just going to stay there. That's as much entropy as it can have. It's going to stay there. Otherwise, entropy increases until it reaches equilibrium. So this is the formal way of thinking about second law of thermodynamics. We kind of already know this, right? This is really an agreement with what we already know about thermodynamics. This is now just relating it to entropy, which we previously hadn't talked about. There are two interesting results of this, again relating back to what we've been talking about in this sequence of videos. When we have two systems at different temperatures interact, so again like our two gases with a membrane in between them in a well-insulated box, we know that heat energy is transferred from the hotter to colder. And again, spontaneously here means randomly. I don't have to go in with tweezers and move it myself. It will just automatically happen due to random processes. We don't see heat energy transferred from colder to the hotter. And again, because if it did, this would actually decrease entropy. It would drive the system from thermal equilibrium. So again, this is in perfect agreement with everything else we've studied. The second case goes back to our idea of irreversible processes. The increase of entropy is an irreversible process, since we don't, for instance, ever see entropy decreasing naturally. What this means is that we can actually define time. That if you have the entropy of an isolated system increasing, that is the future, right? And this is where we can go back to the car crash. For instance, think about a glass breaking. I have a glass in my hand, I drop it, it crashes and it breaks. Originally, those pieces were fairly ordered. They were together in a glass shape. Now my glass has shattered into many, many, many pieces. It's much more disordered. You know that if I play that video backwards, it obviously looks backwards. This is how we actually can discuss the flow of time. So entropy in thermodynamics is what allows us to really know that the flow of time matters. This is something that can be a deeply philosophical question, but this is one of the first times we see it come up in physics, and it's really one of the most definite places that the flow of time comes up. So with that, the lecture videos for this semester finishes.